Hello everyone, welcome to the physics classroom. My name is Deepak Subedi and I'm a physics teacher. Last time we discussed an application of Biot and Savart's law in which we determine the magnetic field at the center of a circular current carrying coil. Today we are going to discuss another application of Biot and Savart's law in which we are going to determine the magnetic field at the axis of a circular current carrying coil. Here I'll show you a circular coil. It is a circular coil and this marker represents the axis of this circular coil. We have to find out the magnetic field at any point on the axis of this circular coil. Now let's represent this circular coil in a diagram. The circular coil is represented by this circle in this diagram. The circle has center O and its radius is A. I amount of current is flowing in anti-clockwise direction in this circle. A point P is taken at distance x from the center of the circle where the magnetic field is to be determined. Here xy and x dash y dash are two small sections of the conductor having a small length dl. Similarly, alpha is the angle made by line joining DL and point P with the axis, and theta is the angle made by line joining DL and P with the small length DL. Here, small r is the distance between point P and small section of the conductor DL, which is equal to root under a square plus x square, which can be obtained by using Pythagoras theorem. Now using Biot and Savart's law, small magnetic field at point P due to the small length dl of this section xy is given by, according to Biot-Savart's law, magnetic field at point P due to the small element xy of the coil is given by, so according to Biot and Savart's law, small magnetic field dB, this becomes equal to mu naught by 4 pi I dl sine theta divided by r square. Here the value of theta is always 90, that's why I put 90 instead of this theta. Then dB is equal to mu naught by 4 pi I dl sine 90 divided by r square, since theta is equal to 90 degree, therefore dB is equal to mu naught by 4 pi I dl divided by r square. This is equation number 1. Now I'll show you why the value of theta is 90 here. As you can see here, it is a circular coil. This is a circular coil and this is the tangent at the small section of the circular coil, and this is point P, and this is angle theta, which is the angle between point P and the tangent or small section of the conductor. As you can see, this is always 90 degree. That's why we put theta is equal to 90 here. Now let's find out the direction of magnetic field at point P. As I have already stated that the direction of magnetic field is always perpendicular to the plane joining the point and the small section of the conductor. And the plane formed by point P and small section of the conductor is, as you can see, this is the plane. This is the plane which is formed by the line joining point P and small section of the conductor. Now using right hand fist rule, the direction of magnetic field is in the direction of thumb. Since the current is flowing in anti-clockwise direction in this conductor, so these fingers, this rest of the fingers represent the direction of current, and thumb represents the direction of magnetic field at this point. That's why magnetic field is directed perpendicular to the plane which is formed by this small section of the conductor and this point P, and this thumb gives the direction of magnetic field which is perpendicular to this plane. Now I'll draw the direction of magnetic field here. The direction of magnetic field should be perpendicular to the plane joining the point and the small section of the conductor. So this is the direction of magnetic field. This is the direction of magnetic field. And in the similar way in the lower section, small magnetic field dB is produced here due to the small section x dash y dash of the conductor in the lower section. And in the lower section, magnetic field is directed in this direction, perpendicular to the plane joining point P and small section of the conductor. Now here, this is also dB, and this angle also becomes equal to theta. This is also theta. This angle is also alpha. You can calculate yourself using geometry. This is also alpha. Now resolving this dB into components, this becomes dB cos alpha, and this is also dB cos alpha, and this component is dB sin alpha. Now here at point P, these two components, dB cos alpha and dB cos alpha, these two components are acting in two opposite directions, vertically opposite directions. That's why these two components get cancelled out. And the only component acting at this point is dB sin alpha, which is along the axis of the conductor. That's why total magnetic field at point P, which is on the axis of the conductor, is dB sin alpha. So total magnetic field at point P due to the circular coil is dB sin alpha. In this case, total magnetic field at point P, which is dB sin alpha, which is due to the only small section XY of the conductor, not due to the whole circular conductor. This is only due to the small section of the conductor. Now we have to find out total magnetic field at point P due to the whole circular conductor. For that, we have to integrate the magnetic field at point P along the length of the conductor, that is along the circumference of this coil. Now total magnetic field at point P along the axis of the conductor can be calculated as, let's calculate that, magnetic field at point P along the axis of the conductor due to the small element XY of the coil is given by B is equal to, now it becomes dB sin alpha. Now we find total magnetic field at point P along the axis by integrating this along the circumference of the conductor. Now total magnetic field at point P becomes this total magnetic field. This is given by the integration of this equation from 0 to the circumference of the coil, that is circumference is 2 pi times radius of the circle, and A is the radius of this circle. That's why 0 to 2 pi A dB sin alpha. Now we can use equation number 1. Here we can replace dB, and dB is equal to mu naught by 4 pi ideal divided by r square. We can put this value in this equation. Now this becomes equal to 0 to 2 pi a mu naught by 4 pi ideal divided by r square into sine alpha. Here all the terms are constant except this dl. That's why we take out all the terms out from the integration. That's why this becomes equal to mu naught by 4 pi I sine alpha divided by r square, and only dl remains inside the integration. Now doing further calculation, this is equal to mu naught by 4 pi I sine alpha divided by r square, and integration of dl is l, and it ranges from 0 to 2 pi a. Now we have to put the values of the limit in this l instead of this l. That's why mu naught by 4 pi I sine alpha divided by r square, and instead of l we put 2 pi a, and lower limit is 0. That's why this becomes equal to mu naught by 4 pi I sine alpha divided by r square into 2 pi a. Here this pi cancels out, 2 to the 4. Then this becomes equal to mu naught I a sine alpha divided by 2 r square. Now in this triangle COP we take sine alpha, because we have sine alpha this term in this equation. That's why we take this triangle COP. In triangle COP, taking sine alpha, you can see sine alpha is equal to perpendicular divided by hypotenuse. So perpendicular is a here and hypotenuse is this r. That's why sine alpha is equal to a divided by r. Now using this value of sine alpha in this equation, we get b is equal to mu naught I a divided by 2 r square into a divided by r. This becomes equal to mu naught I a square divided by 2 r cube. Again we know the value of r from here. That's why I put r is equal to a square plus x square in this equation. That's why this becomes equal to b is equal to mu naught I a square divided by 2 root under a square plus x square to the power 3. That's why this becomes equal to b is equal to mu naught I a square divided by 2 a square plus x square to the power 3 by 2. This gives the magnetic field at point P along the axis due to a single coil. If there are n number of circular coil, then we have to multiply this magnetic field by the number of coils. Then if there are n number of circular coils, number of circular coils, then this becomes equal to b is equal to, we just have to multiply by the number of coils, then mu naught n I a square divided by 2 a square plus x square to the power 3 by 2. Now let's see if this point P lies at the center of this circular coil. That means this point P lies at point O. Then the value of x becomes 0. Then let's see what happens when point P lies at the center of the coil. Center of the coil, then x is equal to 0, and this B becomes equal to mu naught n I a square divided by 2 a square plus 0 to the power 3 by 2. This becomes equal to mu naught n I a square divided by 2a cube, and this becomes equal to this is equal to mu naught n I divided by 2a. This is the expression when point P lies at the center of the circular coil. This is the expression for the magnetic field at the center of a circular current carrying coil, which we did in the previous class. Now let's see its second case. In its second case, we take this point P very away, far away from the center of this coil. In that case, case 2, when point P lies far away from the center of the coil. In that condition, this term a square plus x square, this becomes nearly equal to x square, because in that case the distance between the center of the circular coil and point P is very large. That's why in that case, in comparison to the distance between the center of the coil and point P, the radius of this circular coil becomes negligible. That's why we take a square plus x square, this nearly equal to x square. Now using this term in this equation, we get B is equal to, this becomes equal to mu naught n I a square divided by 2. We just put x square in place of a square plus x square, and that's why x square to the power 3 by 2, and this 2 get cancelled out. Therefore in this case, B becomes equal to mu naught n I a square divided by 2x cube. In this way, we calculated the magnetic field at the axis of a circular current carrying coil. Next time I'll be coming with another new topic. Till then, see you. Goodbye. Take care.